So now we've built out some Taylor series at our disposal. Let's revisit the idea of an application, and let's see if we can't use a Maclaurin series to great effect. Well, here we're going to, by building a Taylor table, we're going to find the Taylor series for cosine at 0, that's a Maclaurin series, and we're going to use the first two terms to approximate something you don't know the answer to. Cosine of 5 degrees. You could put it in your calculator if you want. We'll compare that in just a moment. But I want to use Taylor series to do it, and then I want to ask a question of the Taylor series, taking only two terms of the Taylor series to approximate this value. How good is that approximation? Is it off by a lot of decimal places or only a few? Let's see how this would work out. For starters, if you carry out this exact procedure we did up here, but instead of sine, you did it with cosine, I encourage you, pause the video and do that. It's a good little exercise. But the first thing we'll have is, we'll come to this conclusion. Cosine of x is the series, well, it's almost exactly this, but predictably, instead of surviving the sines, you survive the, instead of surviving cosines, you have surviving sines. And so instead of basically surviving the odd numbers, you're surviving the even. So this is going to be negative 1 to the n over 2n factorial. Those are even numbers times x to the 2n. We'll also need in this problem that degrees probably aren't the right unit. We'll probably want it to be in radians. So we'll also quickly take 5 degrees, and we'll convert 5 degrees into radians by multiplying by the appropriate conversion factor from trigonometry, namely pi radians is the same as 180 degrees. We will cancel the associated unit conversion, a la what you do in chemistry when you want to look at unit conversion. And we're left with, in this case, 5 pi over 180 radians, which will simplify into just pi over 36. So, what does that mean? That means that cosine of 5 degrees, we now recognize the same as cosine of pi over 36 once we're in radian world. And if I use the associated Taylor expansion that I have here, I'm working with the series starting at 0 of negative 1 to the n over 2n factorial, but now my x is pi over 36. I want to do all this using the first two terms, so that means that if I want to find an approximation of cosine 5 degrees, this is approximately the first two terms of this series. And if I plug in n equals 0, n equals 1, and I write those out, I'll end up getting 1 minus 1/2 times pi over 36 squared. Again, this is n equals 0, this is n equals 1, so we have two terms. And if you take out your calculator and you verify this computation real quick, which is pretty easy to do, there's nothing high-powered or technical. You can even use a 4-function calculator to do that. This is going to be about 0.99619222823, so on. And that's fine. This is cosine 5 degrees, apparently. But is this a good approximation? That's really the question. If you're doing this in a real context, a sincere, genuine, physics-based context, you need to find the cosine of a bunch of different angles. Is this a sufficient number to work with, or do you need better approximation? Is this off by 4 decimal places? 9 decimal places? Well, it turns out that we can actually detect that to some regard, namely because this series that we just built, conspicuously, right here, it's alternating. That means we have access to the alternating series error estimation. And if you go back to that concept and you apply it here, we can observe that the error committed by adding up to the first power we know is less than the next non-alternating component. And that means if I look at this series and I look at the non-alternating bit and I plug in 2, that's going to be 1 over 4 factorial times pi over 36 to the 4th. And if you compute that, you're going to get about 0.00000. That's 5 zeros. 2, 4, 1, 6, etc. And what that means is that suggests that the approximation that I'm working with right here is accurate to the actual value cosine 5 degrees up to 1, 2, 3, 4, 5 decimal places. That this and the real value differ by this small amount. And by modern computing, of course, you can come over here and you can look up the fact, you take your calculator, compute cosine 5 degrees directly, and we know that cosine 5 degrees is about 0.9961946918, etc. And we can observe that, yes, indeed, up to the first 5 decimal places, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, indeed, the two-term Taylor approximation is accurate to the actual answer up to the 5 decimal places prescribed by the alternating series error estimation. And that is powerful. This is exactly what you would do, and honestly, this is what the computer is doing in the background when it wants to compute things like cosine 5 degrees to some particular expansion. It's passing to a Taylor series. And so if you know how many degrees, how close to you want your accuracy to be, you can determine how many terms of your Taylor series you need to adopt in order to make that happen. This right here, it might not be obvious, but this example right here is the point of this entire chapter, of this entire class, more or less, is that in the real world, computing things mathematically is hard. This value is computationally expensive to get accurate out to so many decimal places. But truncating a power series and evaluating a second-degree polynomial is way cheaper from a computational standpoint, and Taylor series tells you exactly how to go from computationally expensive to computationally cheap with exactly the amount of accuracy you need for your physical system. We're going to look at more examples of this as time goes on, but that is a powerful concept. With that said, let's return back to the conversations we were having in terms of collecting more Taylor series. Hopefully we're convinced this actually seems to have some good use cases. For example, here I want to find the Taylor series for the function lnx, but I want it centered at 2. There's a couple of ways to do this. You could build a Taylor table, or you can do algebraic shenanigans in the vein of what we did in section 9.7. In this case, maybe let's go ahead and show, actually there's a third way to do this. You could look at 1 over x and you can integrate it. So there's 3 ways to do this. Let's do, say, algebraic shenanigans for this one. So if I start with ln x, I want it centered at 2, so I'm going to opt to add 2 and subtract 2. If I factor out a 2 inside the log, I'm left with 1 plus x minus 2 over 2 inside the log. This, of course, is a product, so we can hit this with the product rule as far as properties of logarithms go. And I'll get ln of 2 plus ln of 1 plus x minus 2 over 2. And now what I'm going to do is I'm going to look at this series, and this is ln of 1 plus something. For the purposes of this class, you are going to be more than welcome to take advantage of the associated Taylor-Maclaurin sheet, and from that, lifted from our section 9.7 conversations, we have access to the ln of 1 plus something. Go back to section 9.7. We covered this at some point. And if we import that, we know this is equal to ln 2 plus. This gives us the series starting at 1. Oh, I said we could integrate 1 over x. That is true, but probably what we could do is differentiate this to get 1 over x instead. So we wouldn't want to, we would want to differentiate this to get 1 over x and integrate 1 over x to get this. In any case, we get the series starting at 1 of negative 1 to the n plus 1 over n times whatever the value is that you have here. And in this case, it happens to be x minus 2 over 2 to the n. This is what we would have gotten in section 9.7. And so here we have ln 2 plus the series starting at 1 of negative 1 to the n plus 1 over n times 2 to the n times x minus 2 to the n. And so all of this right here, this approach that we have here, is using section 9.7 results. That's the fact that ln of 1 plus a thing is equal to this series. But the observation we're making here is that I could have done this using Taylor tables now. So if I come over here, I could have instead looked at n values. I could have looked at derivative values for ln of x. If I don't differentiate at all, I get ln. Differentiate once, I get 1 over x, which is x to the negative 1. Do it again, I get negative x to the negative 1. Do it again, I get negative 1 times negative 1 to the x negative 2, and so on. This is very similar to the first problem or one of the earlier problems we did in this conversation. Invariably, for n, we're going to end up with n plus 1 copies of negative 1. We end up with, as you can see here, we get negative 1, negative 2, so we're getting a factorial, n minus 1 factorial, all over x to the, this should have been a minus 2. Whoops. This would have been a 3, so this should have been a 2. So this, we'll just rewrite this. So this is going to give me negative 2, negative 3, x to the negative 4 for n equals 4. So we're going to get negative 1 to the n plus 1, n minus 1 factorial, and then on the bottom we get an x to the n. And you might be asking, okay, this is all great. Where in the world did this ln2 come from? Well, remember, in section 9.7, this ln2 came from integration. We had to figure out what the extra c value was. So that's where this came from in 9.7. Here in the Taylor table, it's coming from this first row, because this pattern only holds for n greater than or equal to 1. This has to be its own object, so that C0 just ends up being ln2. And I'll leave the rest of these details for you to work out if you'd like to pause the video, but the idea is you'll get the exact same answer that we have over here. The n value comes from dividing this by n factorial, and so on. So we're again just linking what we've done in this conversation, the Taylor table, with what we have done in previous conversations on power series. Okay, let's continue the journey. Let's look at this. We have Taylor series generated by f of x equals e to the x at x equals 2. Interestingly here, we've already talked about a Maclaurin series for e to the x right here. So this is e to the x at 0. We know that that's equal to this series, x to the n over n factorial. So if I wanted to build a Taylor series, but now centered at 2, I could build a whole Taylor table on its own. But once I know the Maclaurin, I can do algebraic shenanigans like this in order to find it. So let me show you what I mean. If I want to find a Taylor expansion at a equals 2, all I have to do is take e to the x. Within the function, near the variable, I have to add and subtract 2. Properties of exponents says this is e squared times e to the x minus 2. And now this series has as its inside x minus 2. So if I already know exponentials look like a series starting at 0 of the variable to the n over n factorial, the new variable at play isn't x, now it's x minus 2. We still have e squared out here. So if I put it all together, I have a series now starting at 0 of e squared over n factorial times x minus 2 to the n. If you don't like the algebraic shenanigans I'm playing here, I do want to just impress upon you, or you can build a Taylor table. That's perfectly fine. Nothing is stopping us from building a Taylor table. So this is a series centered at 2. We use the Maclaurin series to get here. But what I want to investigate is if this is the Taylor table at 2, if I talk about the Maclaurin series for e to the x, I get e to the x equals the sum n equals 0 to infinity of x to the n over n factorial. Technically speaking, e to the x is both equal to this Taylor expansion and this Maclaurin expansion at the same time. If you work out the interval of convergence for the exponential, you'll find that it's everything. So both of these will converge to the exponential. But sometimes one is better than the other. For example, if I really wanted to compute e to the 2.01, of course, this is me plugging in 2.01. This is surprisingly close to the center I chose here. What we're going to find is that the perk of changing your center to a different value from 0 is that when the center you choose is close to the value you desire, then the corresponding series converges faster, and therefore you need less terms of it to reach a good approximation. Let me show you what I mean. Here, if I plug in 2.01 into, say, the Taylor series, I'm going to get e squared over n factorial times x minus 2 to the n, and I'm going to plug in x equals 2.01. This is the series, let's see, we're going to get e squared over n factorial, then what? Plug in 2.01. 2.01 minus 2 is 0.01, which is 100th. That's a really, really, really small number. Look at that geometric ratio here. That is going to 0 really fast. Whereas over here, if I were to take the Maclaurin series and plug in, so we have x to the n over n factorial, and plug in x equals 2.01. This is just going to come up with the series 2.01 to the n over n factorial. And both of these will converge, yes, But the main difference is that this will converge very quickly, whereas this over here will converge slowly. So if you're working with a physical system and you want to take, like we had up here, only 2 terms instead of having to take 42 terms in order to get your approximation with a sufficient amount of accuracy, you're going to want to use the series that converges quickly. That way the tail is smaller at an earlier point. And what that means is that when you want to plug in values that are, in this case, close to 2, it's better to use a Taylor series centered near 2 or at 2 as opposed to a Maclaurin series, even though both of them will converge. One converges faster and hence has more utility. Okay, at this juncture, let's continue our journey and we're going to look at just a handful of additional examples. At this point, we're mostly just interested in what can we use Taylor series to do? What are its use cases? For example, here I want to use a 4th order Taylor polynomial, so I'm going to go up to a degree 2 for sine of x. But I want to approximate sine of 91 degrees, so therefore I'm going to actively choose a Taylor series centered at 90 because it's close to the object I'm trying to approximate. That does mean I cannot use the Maclaurin series, which we already saw earlier. I'm going to have to recreate this. But that's okay, it's not so bad. What I can do here is observe that, you know what, actually, maybe we can use a little trigonometry here. I could build a Taylor table, but maybe I don't have to. What if we did some algebraic shenanigans? For example, sine of x, I want to center it at pi over 2, right? So if I want to take sine of x and center it at pi over 2, I could just do a phase shift. And if I did a phase shift, that could be really, really useful. But maybe, now that I say it out loud, maybe we do just do the Taylor table. It's in the spirit of what we're doing in this section, right? So let's do the Taylor table. And I'll just say you could have used a phase shift, some observation that, for example, sine of x minus pi over 2 is, of course, the same as cosine of x. Sine and cosine are both the same up to a shift of pi over 2. But let's do the actual Taylor table. We'll start with an index k, because with sine and cosine we know there's a lot of zeros. And as we did before, I take the kth derivative, and then I'm going to take the kth derivative. In this case, I'm going to plug in now pi over 2. So k is 0, 1, 2, 3, 4, etc. The kth derivative is going to be sine of x, cosine of x, negative sine of x, negative cosine of x, and then sine of x. And previously we plugged in 0, which was killing off all of the odd terms, but now we're plugging in pi over 2, so therefore sine of pi over 2 is actually a 1. Oh, previously we were killing off the even terms. Now we're killing off the odd terms. We're going to get 1, 0, negative 1, 0, 1, etc. So indeed, the odd terms are dying, which means the only terms that survive are the even ones, which sounds reminiscent of cosine, but of course we know cosine and sine are related by this phase shift, so that's not surprising. In this case, what we deduce is that sine x, if we switch back to a normal indexing variable n, seems to only record the even powers, so we know we're working with a 2n, namely alternating 2n factorials, but now we want to put x minus the center to the even power. So there you have it, x minus the center. That's exactly the phase shift I was referencing earlier. Okay, if this is our Taylor polynomial centered at 90 degrees, if I want the fourth order Taylor polynomial, which I think we called P4, this is everything up to the fourth degree. So if I plug in n equals 0, I'll get 1, 1, because everything else dies. Plug in n equals 1, I get a x minus pi over 2 squared over 2 factorial. And if I plug in n equals 2, I get x minus pi over 2 to the fourth over 4 factorial. And now that I've gone up to the fourth degree, that's my fourth order Taylor polynomial. So I'm not going to plug in 4, I'm just going up to 4. And this allows us to do sort of what we did earlier. If I want to know sine of 91 degrees, I convert that to radians. I'll let you confirm that that's the same as 91 pi over 180. And if I plug that into this polynomial, P4, at 91 pi over 180, you can verify, and pause the video and compute it yourself if you'd like, you'll get the value 0.999847695, etc. Of course, this value is very close to 1. 91 is very close to 90. If you want to know how accurate this is, since we're working with an alternating series, you can do the alternating series error estimation. And so, this is yet another example of using Taylor series to approximate functions in a very real way, or approximate function values, I should say. Earlier in this conversation, I was able to find, via a Taylor series for E, I was able to find a value for this sum. That was a pretty cool example. That broadened our horizons of what we can compute values for in terms of sums of series that converge. Let's do another one of those. Seemed like a good application. Here my series is a little more complicated though. For example, here I have negative 1 to the n, pi to the 2n, 6 to the 2n, 2n factorial. Although this looks complicated, seeing that 2n factorial in the bottom screams cosine Maclaurin to me. That's what that says to me. This is cosine Maclaurin. So because of that, I'm inclined to try to view this as a cosine power series evaluated at some point. And I can see, indeed, I see those two n's hiding in those powers. So I can observe that this is, for example, exactly the cosine Maclaurin, negative 1 to the n over 2n factorial times x to the 2n. But I'm making my x out to be, in this case, just pi over 6, which is the same as cosine at pi over 6. The interval of convergence, I'll let you confirm or look it up, for cosine is negative infinity to infinity, so therefore plugging in pi over 6 is no issue. And so in this case, I simply get cosine of pi over 6, which I know is equal to root 3 over 2. Maybe a fun exercise, if you'd like to challenge yourself, is, and some of these types of questions are in the practice problems. Well, that did not do what I wanted. If I come in here and I were to take this series in question, a fun alternate version of this is if I were to take that and I were to change the starting value not at 0, if I were to take that starting value and I were to start that starting value at, say, 3, it's a fun little exercise to check that you can validate that sum as well. It's not too hard to show. Essentially what you would get is you'd get the full series minus the 0th, 1st, and 2nd term. So this would be minus, for example, C0 minus C1 x and so on and so forth. Maybe for this exact one I can actually write it out. So this would be the full series, -1. Yeah, let's just write it out. This would be -1 to the n over 2n factorial x to the 2n evaluated at x equals pi over 6. And then I'm going to subtract off the first few terms of the cosine series, which would be -1 minus -x squared over 2 minus x to the 4th over 4 factorial. But of course, all of that is also going to be at pi over 6. And so you'll end up with whatever that answer turns out to be. There are some details to show there, and I'll leave those for you to go through. Or if you'd like to come to my office hours or send me an email, I'm happy to go through them with you as well. Now, the last problem that we're going to cover in this video is one of my favorite applications of this concept. And it's one of the coolest things that you can do with Taylor series in a theoretical way, in a non-applicative way. Well, that's not quite true. You can apply this, but anyway. And because the Taylor series is built off of infinite differentiation, you can actually use it to compute high-order derivatives of functions that have well-known Taylor series. So, for example, here, if I wanted to find the 10th derivative of arctan of this x squared over 3, specifically at x equals 0, that's kind of the important part. This is the signal that you want to use a Maclaurin series. It turns out that you can use a series to get at this question. You do not have to, a la Calc 1, differentiate this 10 times and then plug in 0. That's way too much work. Let me show you how we do this. So the idea is to take arctan of something and then pass to its series. And again, if you look at section 9.7, via integration, we did find a power series for arctan. When we did that, it was equal to -1 to the n over 2n plus 1, starting at 0, times its variable to the 2n plus 1. But in this case, the variable is x squared over 3. So there's x squared over 3. And if we clean this up real quick, we can rewrite this as the series from n equals 0 to infinity, -1 to the n over, let's see, 2n plus 1 times 3 to the 2n plus 1 times x to the power of, let's see, if we go ahead and do the power to a power, we multiply the powers. So when we distribute that 2, we're going to get 4n plus 2. Now, what do we want? We want the 10th derivative of this function, right? So we want the 10th derivative specifically evaluated at 0, but by Taylor's theorem, all the way up here, we know that we have this relationship, that the nth derivative, in this case the 10th derivative at 0, divided by n factorial is equal to c, in this case 10. So if we move n factorial to the other side of that equation, what we're working with is the fact that this is equal to c10 times 10 factorial, where very specifically, and I can't stress this enough, this is the Taylor coefficient. Well, let me be clear. I said, oh, it's the 10th Taylor coefficient. That does not mean it's the 10th one you see. What that means is this is the Taylor coefficient for the 10th power, right? When we talked about the Taylor polynomials, we were talking about the power present in the polynomial. And in this case, much like sine and cosine, which reports only even powers or odd powers, we don't have all powers of x. So we don't want the 10th term, we want the coefficient for the 10th power. So, to that end, we make the following observation. We note that x to the 10, what we're looking for, occurs when Well, the power in question is 4n plus 2. So that occurs when 4n plus 2 is 10, which means 4n is 8, which means n is 2. So it turns out that it's the n equals 2 term of this series that produces the degree 10 term, for which we have as the 10 Taylor coefficient. Thus, what we're working with is the fact that the 10th derivative at 0 is, again, c10 times 10 factorial. This is going to be the coefficient formula. That's going to be, in this case, negative 1 to the n over 2n plus 1 to the times 3 to the 2n plus 1. That's the coefficient formula evaluated specifically at n equals 2 times, of course, 10 factorial. And I won't simplify it, but this turns out to be something like, it looks like 10 factorial over, it looks like 5 times 3 to the 5th. And so this is the power of Taylor series. It allows us to take a 10th order derivative and evaluate it at a point without ever having to take 10 derivatives. And I'll tell you, as I'm doing this problem, I really like this as a theoretical application of Taylor's theorem. And this, along with finding the value of some sums and finding approximate values to function evaluations, I think serve to represent some of the really neat initial applications of Taylor's theorem and Taylor series in general. So that's where we're going to wrap up this conversation. The remainder of this handout is discussed in the next video, in which we take a look at some additional practice problems, and we specifically apply Taylor series to look at approximation efforts as they relate to, say, computing interesting definite integrals. So definitely take a look at some of the homework discussed thus far in any of the given sections. We've covered in this video conversation from sections 9.8, 9.9, 9.10. The next video will continue conversations in these sections. I don't go in the same order the textbook does. That's why this is all given in a slightly different order. I approach this via the direction we just discussed, which in my opinion is a little bit more natural. But of course, you're welcome to take a look at the book and look at some additional problems there. Reach out to me if you have any questions. Otherwise, look at some of the associated homework, take a look at that next video, and I'll catch you all in the next one.